Hi everyone, my name is Daria and welcome back to MoE 101 Guide series. In our last episode, we were able to train our own MoE model on a tiny acceleration node, or some people even reported they were able to train it on their laptop. We only used 4 experts there, but production systems like DeepSeek V3 use hundreds of experts. Try scaling to their sizes with our previous simple implementation, and you will quickly run out of memory. In this episode, we will talk in depth about the scaling challenge. First, we will discuss how GPU approaches this problem and what are its limitations. And then, we will talk about how Cerebras wafer scale engine tackles this issue. Let's first start by defining the problem. If you take our previous implementation from part 3 and try to scale number of experts, let's say from 4 to 64, just launch your training run like I do and see what happens. It usually takes some time for us to hit the problem. I'm going to skip through the steps and you will see the final issue. We are running out of memory, and now let's understand why. If you guys remember, in part 3, we defined a function called expert mixing. And we warned you that this function is only used for teaching purposes, and it's not efficient. Let's take a closer look. Why? If you look at the line 215, you will see that we have a loop across all experts. But wait a minute. MoE is supposed to activate only a portion of the experts for a given token, not all of them. So why do we have to load all these experts into the memory? Well, as you remember, in part 2 of the MoE series, we discussed that industry standard routing is not deterministic, and hence it is not possible to predict which token will go to which expert in advance. So we have to load all of these experts into the memory, just because we might need them later. Think about it this way. DeepSeek V3 only used 40 billion active parameters for any given token, but it had 600 billion of total parameters, and they had to load all of them in order to train the model. This is why you are hitting this out of the memory issue with a simple implementation like ours. Usually when you run a model on a GPU and you hit an out-of-memory issue, there are multiple ways to distribute your model weights into multiple GPU devices so you can actually train it. We're going to specifically look at the expert parallelism. Expert parallelism is defined on the figure 8, and it's usually combined with other types of model parallelism, like tensor parallelism or pipeline, etc. What happens with expert parallelism in particular? Let's place separate expert networks on separate GPU devices and run them in parallel. Here's how it's going to work. When a batch of tokens moves to the router network, the router then decides which experts are best positioned to process each token in the batch. Then we perform an all-to-all communication that distributes those tokens to the particular experts and to their devices. Then each expert runs their tokens in parallel. Afterwards, we need to perform this additional expert mixing operation. And for that, we need to run another all-to-all communication operation so that activated expert outputs for a given token reside on the same device. Expert parallelism is a way for us to be able to actually train MoE models at scale. However, it has its limitations. One, we actually assume with expert parallelism that each expert in a network receives approximately the same amount of data and distributes the batch equally. However, we don't actually meet this in practice. As you remember in part 2 of the series, we showed that industry standard routing does not guarantee balance. We actually want each expert to specialize in something. and hence it might require a disproportional amount of data for each expert network to work with. Because of that, some of your GPU devices with experts receiving less number of tokens will stay idle and overall utilization of the cluster will be low. In addition to that, as we continue increasing number of experts, it becomes more compute efficient to make each expert smaller in size and activate more of them. Because of that, communication to computation ratio with expert parallelism worsens. We spend most of our time moving the data around and not computing useful operations in expert networks. Great, so now you know how you can scale and train MoE models on the GPU devices with expert parallelism. But how do other accelerators handle MoE models? Let's take a look at Cerebras wafer scale engine in particular. Here are some of the important numbers about the CS3 machine that you can compare to the GPUs. One parameter that I want to highlight in particular is the amount of on-chip memory that we have on the CS3 machine. We have 44 gigabytes of on-chip memory. You can think about it as SRAM on the GPU. And as you remember, the most latest GPU devices have something on the order of 50 megabytes. So it's almost 1000x less. With that amount of on-chip memory, we can actually fit a very big model on the chip itself without requiring any type of model parallelism. For the models that exceed the capacity of the wafer, we actually induce a specific type of the execution called wait streaming. With wait streaming, we disaggregate the computation from the storage and create a separate node called Memory X that we connect directly to the chip. Memory X will contain most of our heavy weight tensors, and the chip itself won't store them at any given time. What we do, once the chip calculates the gradients, it streams it to the Memory X node to update the weights after the particular gradient step. So you see where I'm going with this? We essentially can train trillion parameter models with a single CS3 machine without expert parallelism or any other type of model parallelism. But because it's possible to fit huge models on a single CS3 machine, doesn't mean it's going to train efficiently. Remember, in the part 1 of this series, we noted that MoE models allows us to save a lot of flops and train them faster compared to the dense networks. In particular, we talked about that 32 experts allows us to save something on par with 60% of flops and train models 3 times faster compared to the dense network to the same loss. Now, let's actually run an experiment and verify what happens with the throughput. I'm going to take Qwen3 model, one of the recent releases, and vary its sparsity levels and observe how it changes the throughput on the CS3 machine. Here we can see how the speed of the MoE network changes compared to the dense network with the same number of active parameters. What we expect is to see approximately the same throughput between an MoE network with a dense network because we spend the same amount of flops. But we are actually seeing slowdown. On the left side, we are sweeping number of experts and fixing the number of active experts at 8. Increasing the number of experts or going to the right induces more sparsity into the MoE model. On the right side of the picture, we are fixing the total number of experts at 128 and vary the number of active experts per token. Going lower top K makes the model sparser, and you can see that we are hitting 7x slowdown compared to the dense network. What it means is that we are not going to train MoE model faster than a dense network, and we are not going to translate those flops reductions into the actual wall clock time reductions, unfortunately. So let's try to understand where is the problem. essentially what we're seeing here is the compute utilization problem. We have a lot of compute, a lot of memory, but somehow are not efficiently utilizing it. An important part to note is for each expert network, we have to subdivide the batch size. So each expert will specialize on its own portion of the batch. Because of that, and especially when you make each expert smaller in size, the amount of compute that we perform on the expert networks is very minimum. But if we look at other layers in a network, we will notice that the attention layer does not subdivide the batch size, and big batches actually hurt its performance a lot. Why? Because attention layers are actually activation memory bound. You are increasing activation memory quadratically as you increase the sequence length of the network. As a result, we have expert layers that are starving for more data, just wasting compute resources assigned to them, staying idle. At the same time, attention layers are struggling to process more data. They cannot work very well with big batches of data. One of the simplest ways to solve this problem is to separate the batch size for attention layer and for the FFN block. Attention layers requires smaller batch size to be more efficient, and expert networks requires larger. Let's actually implement it. On Cerebras CS3 machines, we created a technique called batch styling on attention. Let's assume that we have some input data, and it has the batch size B as sequence length and some hidden dimension. We need to move it to the attention layer. So before we throw a huge batch into the attention layer, let's tile it into G separate blocks and process them in parallel. This way, attention will work more efficiently because it will not have to store a huge tensors coming from the softmax. At the same time, our expert networks want bigger batch size. So after the attention layer processes those G tiles, we're going to concatenate them back into the bigger batch size and move them to the expert networks. This way, experts will have G more data to work with, and you can configure this G according to your setup. This technique is actually inspired by flash attention that is efficient on the GPUs. Flash attention tiles on the sequence dimension to solve the same activation memory issue with attention. Here, we expanded this approach and introduce a bigger batch size for the expert networks as well. So then we can balance the compute utilization between attention layer and the expert networks themselves. Cool. So let's run some experiments to see how it actually works in practice. Remember, our default MoE implementation was not performing well. It was actually slower than the dense network for the same number of flops. I outline it as a baseline here, so the red curve. Now, I also ran experiments with the BTA and scale it across multiple dimensions as well, number of experts or number of active experts. So you can see that with BTA, we're actually matching our expectation. For the same number of flops or the same number of active parameters, BTA's performance is matching our dense model performance and staying flat across different sparsity levels. So this allows us to actually not just fit trillion parameter scale models on a single CS3 machine, but also train them efficiently. Now, BTA is not a silver bullet, and it's just one feature in a broader optimization toolkit that we use on CS3 machines. It can be easily combined with other features like FP8 compression on the weights from DeepSeek V3, or even expert parallelism that we use on the GPUs. There, you simply assign different experts or different groups of experts to separate WC machines and run them in parallel. And that's actually it. You now know how to scale MoE models on the real hardware. So let's recap what we've learned so far in this series. In the part 1, you learned about MoE fundamentals. In the part 2, you understood how to select the best router suited for your workload. In the part 3, you were able to train an actual MoE model from scratch and make it work. And now you also solved a compute utilization issue on Cerebras hardware. In the next episode, we are going to switch our focus from training to deployment and sharing with you practical tools that you can use to make informed decisions whether to deploy an MoE model or stick to the dense architecture. Thank you.